So maximum, minimum problems, which are key problems in mathematics. I mean, trying to maximise, minimise different things. So if we're thinking about the graph, maximum and minimum is, we're talking about the vertex. When we're talking about practical problems, sometimes they might not be interested in what the actual maximum value is. It might be the dimensions that give that, because they might want to know how much material they need to make the maximum area or something like that, in which case it would be the x value they're interested in. So that's why I say you've got to read the question carefully to see whether it's the dimensions or the x value that they're interested in, or the actual final maximum area or the y value. So, well, this is just a straight quadratic. Find the maximum value of, and as I was saying the other day, we don't actually need to find the axis of symmetry. We can find the discriminant and do it that way. So we need to find the y value of the vertex. Now, I could do it by completing the square, and then that tells me once that's completed, there we go, we end up with, it's been shifted down 4 and 11/12. So there's our maximum value. Or we could use the discriminant idea and say, well, minus the discriminant on 4a. So minus 59 over 4 times negative 3, which is 12. And we get the same answer. Or, of course, we could just find the axis of symmetry and sub that in as well, which is probably the longest way of doing it. Well, let's look at a practical problem. So we've got a rectangle. We know its perimeter is 64 centimetres. What dimensions would we have for maximum area? So maybe we've got a piece of rope that's 64 centimetres long, and we want to turn it into a rectangle, but we want to capture the greatest area. So, okay, there's a rectangle. I'll call the side S very creatively, which means the other side I know must be 32 minus S, because the whole thing's going to add up to be 64. And so my quadratic then is just for area is S times 32 minus S. And what we're saying, it's interested in what dimensions. So the actual area we're not interested in. So in this case, I don't really care what the y value of the vertex is. It's the x value of the vertex I'm interested in, because that'll tell me the S, or the dimensions of the rectangle. So, okay, that would be, if I do it via completing the square, we can see it's 16 centimetres for S. Turns out the square gives us the maximum area. You'll find that with all shapes, actually. The perfect shape will always maximise the area. So an equilateral triangle would maximise an area if we're talking about triangles. That's if I did it that way. Could have used axis of symmetry, minus b on 2a. Done that way. Anyway, not a lot really needs to be said about that. It's just finding either the x value or the y value of the vertex in order to solve the problem. The trickiest part usually is actually coming up with the equation itself. Sometimes that's not straightforward. Anyway, multiples of 3. Ooh.